בוקר טוב, שומעים? בוקר טוב לכולם. היום זה רגע מרגש ושמח שיובל מציג את עבודת הדוקטורט שלו. יובל עשה את כל התארים שלו פה באוניברסיטה, תואר ראשון פה במכון, תואר ראשון נדמה לי שילבת גם עם היסטוריה אם אני זוכרת, ואחרי זה בתואר שני בתוכנית להידרולוגיה שבעצם הפך לדוקטורט ישיר, ובקרוב בסביבות ינואר יסיים את הדוקטורט, ואתם תראו את הרבה מאוד דברים מאוד מאוד מעניינים מהדוקטורט, דברים שקשורים בעצם לקשר בין מטאורולוגיה ובעיקר סופות גשם קיצוניות ותהליכים של עיצוב פני השטח בסקלות גיאולוגיות, ואני יכולה להגיד שיובל לא יכול להציג את כל התוצאות שלו מהמחקר, כי הוא עשה עוד איזה 2 דוקטורטים במקביל שלא יוצגו, אבל הם גם קשורים בעצם לתהליכי פני שטח, גם יותר מודרניים. זהו, אז ניתן, אולי נגיד גם שיש 5 מאמרים שיובל, הכותב הראשון שכבר יצאו מהדוקטורט הזה, ועוד 2 שהוא שותף, אז יש גם באמת תוצר מדעי חשוב ומעניין. זהו, יובל עכשיו בוא נשמע את ההרצאה.
Okay. So, hi everybody. I'm very happy and excited to be here and to share with you the research that I've been leading in the past, let's say, 5 years. And I want to begin with an important part. Okay. And first of all, to say thank you. So, first to my advisors, Efrat, Yehuda, and Itai. Each of them contribute to my research in his unique way. And I feel really fortunate to study and do research in the intersect of 3 of them. I think that for me it was the best way to learn science. From the very beginning, I felt that they care about my progress, and this is my progression is in their top priority. Also thanks to lab mates and all the unofficial mentors from the lab and also other friends from all over that helped me to do research, that accepted to skip lunch sometimes and count rocks under the sun. Thanks for helpful researchers from this institute and other abroad for the discussion and unofficial mentoring. Thanks for all the administrative staff that helped me to go all the bureaucratic as smooth as possible. Obviously, thanks for the funding that make life easier, and to my family and Nuni for the endless support. Okay, so the impact of climate on landscape is in some sense, and the basic level can be intuitive. Some of the impacts of climate on the landscape are more pervasive and long-term, and like affecting water resources and soil erosion, but others are more short-term and could be catastrophic, like landslides, rock falls, and flash floods. All these processes have some geomorphic imprints, or they trigger some geomorphic changes on the landscape. Therefore, we can see the landscape as an archive of geomorphic changes in response to an external forcing. One of them is climate. And in principle or in theory, we should be able to inverse the landscape in quantitatively way to the environmental changes through time. This could help us to manage better the landscape under current and also future climatic changes and other external forcings. When researchers all over the world trying to evaluate erosion impact over the long term, they are usually use mean climatic properties. And a clear-cut example for that is from a very non-dry environment on Earth, which is an island called Kauai in the Hawaii island. And across this island, there is a significant difference in the mean annual rainfall that goes from about 500 millimeters in the eastern part of the island to more than 9 meters in the central part of the island. This significant change in annual rainfall found to be as a very good explanatory variable to erosion coefficient, which is some coefficient that controls the rate in which rivers are drained this island. And as you can see from here, that the erosion coefficient of these rivers is increasing systematically with a very significant gradient in mean annual rainfall. But over this, so from this clear-cut example, we can learn that where the gradient in annual rainfall is very significant. You can actually, within this small island, you can measure about 70% of the mean annual rainfall all over the globe. You can find it somewhere in this island. Erosion coefficient is very related to this gradient. But, by fact, most of the lands on Earth looks much more similar to this. I don't know if most, but 45% of the lands on Earth looks more similar to this kind of environment. And we can ask ourselves if the mean condition is relevant to what drives the surface processes. And here is an example from Nahal Yael. This is a small watershed located near Eilat. I'm sure that most of you are familiar with it. And I just plotted data that recently published by Lekach and Ezel from 2021. I just naively plotted the data of annual sediment yield for years that have measurements with the mean annual rainfall. And you can see that trying to explain erosion in this small watershed, about 0.5 square kilometers, the mean annual rainfall do a really poor job. And what is the reason for that? So shortly, I will try to mention some complexity in dryland environments. So first, there is very high sensitivity to surface processes. Back 30 or 40 years ago, but also nowadays, people were mentioned or recognized that the behavior of sediment transport index or erosion in drylands is very non-linear related to rainfall according to different feedbacks and threshold events. We found in a paper that I've been in a work in a side project with researchers from the survey and also from Pittsburgh University, we found that erosion coefficient within the desert changed significantly, although there are no significant in time, although we don't recognize significant differences in the mean annual precipitation. And it's been early recognized by Woolman and Gerson, and also recently, that extreme events in deserts are generally much more larger than the mean condition. Therefore, the mean condition is not necessarily what actually drives the processes in this kind of environment. And in other projects that we try to constrain erosion risk in a convective environment, in the Mediterranean climate, we found that, yes, extreme events are in order of magnitude more large than the mean condition. So from here, we should gain some understanding that if we want to deal with what drives surface processes in dry land, we need to focus on higher resolution than let's say, the mean annual or long-term annuals. But this is obviously a complex task. First, because we are trying to capture this kind of small processes that are discontinuous in time and space. Also, it's hard to evaluate the impact of extreme events. And generally, observation in this kind of environment are very sparse and rare. So these are the main challenges that I worked on in my PhD thesis. And I work generally in dry environment, but I'm focused on specific landform, which is hillslope and cliff-related landscapes. So this type of landscape are very common in layered environment worldwide on deserts. And the main mode of erosion in this area is retreating of the cliff. The cliff is comprised of two main units, an upper cap rock resistant layer, and on the bottom of it a lower layer that is much more softer. Sometimes covered or partially covered by sediment that were delivered from the cliff while it's retreated away from the local base level. So the research is surrounded around three main chapters, each chapter by its own, but three of them together trying to bridge aspects of short-term hydrometeorology with long-term geomorphology. And in the first one, we dive into observation, rainfall and runoff and sediment mobilization, and field experiment. In the second chapter, we upscale a bit and we try to quantify hillslope morphology as function of variation, spatial variation in hydroclimatic forcing. And in the last chapter, I will present my effort to generalize the field observation into a numerical scheme, numerical modeling scheme that using numerical experiment to examine different aspects of coupling between rainstorm regime and hillslope erosion in drylands. So the first chapter is focused on a site in the eastern Negev, which is called Tzuk Tamrur. And in this, the aim of this chapter is to characterize the dominant hydrogeomorphic processes and quantify the frequency. And we ask two main questions. First is how often and what are the conditions under which runoff is generated and over the slopes. And second, what is the frequency of erosive event in this type of area. And this is not trivial as this area is ungauged and the record is short, and I will try to show some example of how bridging these gaps. So first of all, the first part of this chapter was aimed to identify runoff generating storms. And we done it using two instruments. One is rainfall radar that used to be situated in Arad. It was a relatively unique radar with very high spatial and temporal resolution. And we use this instrument to track rain fields. We track the cores of high intensity rainfall maps, and we call these cores rain cells. And we track them and calculate their statistics like velocity, maximal 5 minutes intensity, and so on. The second instrument is a time-lapse camera that we use them to observe the field during the storms and to see if runoff is generated or not. So I will show an example of how it looks like. So you can see on the left that how I'm tracking the cells, the rain cells in the radar map, and on the right figure, corresponding picture from the site with a bit runoff that's generating in the lower part during the specific, very short rain cell. So we've done it for 2 years, for about 14 storms, and I will show quickly some example. So this is an example for a storm that didn't produce runoff at the site. You can see that the maximal rainfall intensity, this is what I want you to focus on, is relatively low, about 8 millimeters per hour of the specific cells that cover Tzuk Tamrur. Other storm that did produce runoff at the site is with 22 millimeters per hour. You can see the difference, and also how the cell, the rainfall is precipitated only in a very limited part over the watershed. Another storm is 25 of April 2018, and this is a day before the Tzafit disaster. And this storm also produced runoff at the site with maximal rainfall intensity of 25 millimeters per hour. And not get too much into details, the main conclusion from all the data set that I collected is that runoff generating rain cells are generally slow, and they are characterized by maximal 5 minutes intensity that greater than 22 millimeters per hour. Okay, so up to now it's observation, but as I said, I'm trying to evaluate what is the impact of extreme event, or what is the frequency of the processes, and the observation that we collect are not necessarily have information about events that didn't occur, right, or rare events that didn't happen. So to bridge this gap, we are using a scheme that's called design storm. Design storm are based on IDF curve, which are intensity, duration, frequency curves. These curves relate between the intensity, the duration, and the frequency of rain periods. And based on these curves, or these statistics that come from rain gauges, we design storms. That means storms that typically characterize 5 years or 100-year return period. Okay, so we end up with some storms that are typical for a specific site, but now we need to simulate them somehow in the field to observe what could happen. So the first type of simulation is a physical simulation that we conducted on the slope on Tzuk Tamrur. We use an instrument that's called rainfall simulator. This is a common instrument in, let's say, soil sciences or erosion studies, mostly done in the lab. We try to bring it to the field, and as you can see and maybe imagine, there are some limitations that prevent this or make it hard to do it, but finally we end up in successful experiments, and in the experiment we can generate the design storm over these kind of plots and measure and collect sediment and runoff. So an example of hydrograph during the simulation is up here on the right, but what I want you to focus is on the left side, and what these figures show is combining the experiments and the rainfall observation from the radar, we constrain a threshold for runoff generation, which is 5 minutes rainfall intensity between 14 and 22 millimeters per hour. That means that any rain interval that for 5 minutes that will be greater than this value will generate locally rainfall runoff at the site. Based on rain gauge statistics, we constrain the frequency of this kind of events, which are between 1 to 3 events in a year. This may sound a lot for some of you, but we need to keep in mind that this frequency is for local runoff. That means that runoff, let's say, that produced in the upper part of the slope will not necessarily propagate all the way down and reach the stream, because it can infiltrate if the rain stops. So to quantify the extent of runoff contribution area, we use hydrological modeling, and this time a model that developed by Yair Rinat, and we simulate the same storm, now not physically, but using the computer program. And in colors, what you can see here is the extent of runoff contribution area, which means the upper part of this curve are the maximal extent in which the water drop can travel all the way down and reach the stream. And the key conclusion from here that the frequency of full extent runoff is about 100-year storm. Let's say the 5-year storm, as you can see from this figure, produce runoff only on the middle to lower part of the slope. The last set of analysis in this chapter was to constrain the frequency for sediment mobilization. And for that, we first need to have some information about the sediment at the site. To do it, we measured a lot of clasts along the slope, and what I just illustrate here is grain size measurement correspond to this y-axis and the topography. Then we use the numerical simulation of the flow and calculate the maximal shear stress using the water depth, translated to maximal grain size. This is this curve, the gray curve, which means the maximal grain size that can be transported by the flow at the specific location. If the maximal calculated grain size of specific storm, let's say 100 year, is above the measurements, that means that this storm is effectively can transport the sediment on the slope. And this is what we've done for all the storm that we designed. I just added the lower panel here, and you can see the 100-year curve in black as similar to here. But now shear stress translated into maximal grain size, and you can see that this curve with its uncertainty merges with the measurement of class that colored by blue. That means there can be mobilized by the 100-year storm. So from here we constrain the frequency of sediment mobilization. This is around 100 year. Okay. So to summarize this part so far, we first ask how often and what are the conditions under runoff is generated, and we constrain a threshold, characterize the rain cell properties and the frequency of local and full extent runoff. And the second question deals with the frequency of sediment mobilization, and here we constrain that under present climate, 100-year storm is effectively, or rarer are effectively, could erode the surface. That means that if we are interested in erosive storm, we need to under present climate, focus on extreme events. Okay, the second part of the research is upscaling to 2 more sites along the Ramon Escarpment. So we have in total 3 main study sites within the arid realm. This is important. Everything is within the arid realm. And in this chapter, we ask 3 main questions. First, how do hydroclimatic properties change within this kind of arid environment, if at all? There are systematic differences in the hillslope morphology, and if we can provide some mechanistic explanation for this kind of variation in the morphology. And to do so, we first focus still on Zug Tamrur. So this is a digital elevation model of Zug Tamrur, and we took advantage of the shape of Zug Tamrur, that we can analyze different aspects of it, and aspect-dependent processes, or let's say hillslope asymmetry in general, are vastly studied in soil-covered hillslopes and mostly in wetter environment. But here we try to see if we can see some aspect-dependent processes in arid environment. So the first analysis was to take advantage of talus remnants, or we call them talus flat iron, which has part that used to be connected to the cliff, but not anymore because the cliff has been retreated, and we project their profile, their topographic profile, to estimate the total retreat of the cliff. We've done it for all these profiles surrounding Zug Tamrur and examine if there are any aspect dependency of this process. So what you can see in this map by the yellow and reddish color, that as you go to the south, the colors being darker, that means the retreat is larger, and from this map we conclude that there is some aspect dependence retreat rate in Zug Tamrur with a higher retreat toward the south. Zooming into Zug Tamrur morphology, so the first order differences that we recognize is that the north-facing aspect of Zug Tamrur is much more steeper, and the south relative to the south-facing slope. And we measured sediments, as I described before, and we observed that the north-facing aspect characterized by much coarser grain sizes relative to the south-facing aspect. So this difference in grain size could explain the higher retreat rate in the south-facing slope, because smaller clasts decrease the hydrological threshold for transport, and this may drive a higher retreat rate of the south-facing aspect. Now we can ask from where this difference in cliff weathering originates from. So as Zug Tamrur is located in hyper-arid environment under hot condition, and even considering temperature drop during the Quaternary, it's rarely reaching 0. We conclude that the main factor that governs the bedrock weathering in this site is solar radiation or thermal heating, with obviously a much larger flux of solar heating in the south-facing aspect, which enhance the bedrock weathering and control the overall morphology of Zug Tamrur. Okay, scaling from Zug Tamrur to the central Negev, here we are looking on the digital elevation map of the Ramon Escarpment, and this is about 35 to 40 kilometers escarpment located within the arid realm. And the first thing that we done is a high-resolution topographic analysis. We use aerial LiDAR data with very high resolution to characterize how the cliff gradient and the channel density vary along the cliff. So going from the southwest to the northeast, we observed an increase of the cliff gradient toward the northeast and increase of the channel density beneath the cliffs. Focusing on 2 sites that we study more closely, we recognize also differences in the active taluses morphology. So in the southwest, we observed on longer slopes with a thicker debris cover and a shorter free cliff, while in the northeast, we observed on tall vertical cliff, a very thin sediment cover and the slopes are generally shorter. In terms of rainfall analysis over the Ramon area, we use multiple sources, rain gauges, intensity gauges, and simple rain gauges, just accumulate rainfall, and convection permitting weather model from the IMS. This model know how to solve convective and can provide us rainfall information in relative high resolution. And we use this record to conduct a pixel-based statistical analysis using a statistical analysis that were developed by Francesco Mara, that used to be a researcher here in our lab, but now is in Padova. So based on these tools, we produced, I will first present this map, which presents the 2-year rainfall intensity over Ramon escarpment. So as you can see, the two interested area, the focused area in blue and red, and in the first order, you can see that there are not much differences in the 2-year intensity, although in the mean annual rainfall, the southwestern side is with much higher annual rainfall mean. And the reason for that is the number of events that are larger in the southwest, and I will get to that in a few slides. However, when looking on the 100-year events, then we can see some differences in space. The northeastern part of the escarpment is characterized by much higher rainfall intensity, although it's generally drier, while in the southwestern part, we observe for rare events, lower intensities in general. So we further analyze the rainfall at the site by producing intensity, duration, area frequency curves. Now we account not only for the pixel side, but also for the cell area. And we've done it by, again, pixel-based analysis, but using different ellipses area. And we fitted ellipses that maximize the rain field for each event. And from that, we can calculate statistics that relate also to the area of the cells. And here is an example. I want you to focus on the right side of the slide. So this is an analysis for the 14 square kilometer area. And here we, on reddish color, you can see the eastern side, northeastern side. In the blue colors, you can see the southwestern side. And as you go up in this figure, we increase the return period. And as we go in left in this figure, we are focusing on shorter durations. And for the shorter duration, let's say 10 minutes and 100-year return level, the intensities in the northeast are much higher than in the southeast. And for the rare return period, the difference is reduced, but still remains for long durations. But if we're going to common 2 years return period, the differences are much smaller. When looking on larger area, we still see some differences, but not as much as for the small scale. And from here, the main conclusion can be that there are spatial differences, but they are small scale, probably relate to convective processes that are very much, that are relatively small in terms of tens of square kilometers. From where these differences come from, or what could be explanation for that? So for the increase of rainfall intensity over Mount Ramon, which is the southwestern part of the escarpment, is simply orographic effect. This is common phenomena as enhanced elevation enhance the annual precipitation. But as I mentioned, we see that there is a gradient in the maximal intensity is the opposite direction to the mean annual rainfall. And this trend actually could also be explained by orographic effect. And this is a phenomena that called reverse orographic effect, and is quite, it's become a known thing now. It's observed for example, in the Italian Alps, where elevated area make the short-term intensity to be smaller, although the general annual mean is larger. So the last analysis for this chapter is to try to see, okay, these are the differences in the rainfall in the area. Could it explain the topography or not? So we took the same approach as we done before. We designed storm and simulate them using a hydrological model on the slope. So this is the slope of the southwestern side, and this is for the northeastern side. And points are, or scatters are class measurements. And from here we can see what is the frequency for sediment mobilization. These curves represent the critical grain size for different time periods. And in the northeastern side, we recognize that the frequency of sediment mobilization is between 10 to 50 years, while in the southwest is more than 50 years. And this is somehow could explain the much more dissected northeastern side with thinner debris cover relative to the southwestern side with exceeding the threshold for erosion during much rare storms. Okay, to summarize this part, first we ask if there are changes in climatic properties, and we found that there are changes in aspect, in microclimate, and also gradients in the annual rainfall and the short duration intensity. In the second chapter, we ask if there are differences in the hillslope morphology, and yes, we found that by aspect and also in Ramon between the two sides of the escarpment. And third, we provide some mechanistic explanation for that by analyzing the frequency of exceeding threshold for motion as derived by extreme rainstorms. Okay, the last chapter is trying to bring all the field observation together into and developing numerical tools that could be useful for simulating hillslope surface processes in general in hillslopes worldwide, and to conduct numerical experiment of landscape evolution in response to climatic scenarios. And we done it using, we developed a landscape evolution model. This is a part of mathematical formulation that describe how different processes drive the evolution of the topography over time. And up to date, this is quite, it's become a really common models that observed, but there are only few attempts were used and developed this kind of numerical model in dry environment. In other places, they are usually use the commonly external forces such as the annual mean, rainfall or something like that. Here we are trying to include explicit representation of rainfall and hydrology, and this is rarely done in this field of landscape evolution. So the model setting in general is distinguished between two units, cap rock and a softer layer, and we also include in the model some debris layer, which is a layer that comprises of about, it can be user-defined, but I'm using 30 size fraction of grain sizes. And the model is grid-based. That means that we have many of these cells along the slopes. And I will not get much into details, but as I said, the model includes a full representation of hydrology. Erosion is outcome of different processes operating on the slope, such as sheet flow, slope diffusion, bedrock weathering, and incision. We also include new component of class fragmentation, and two mechanisms of cliff retreat. I will not get into much details, but I will be happy to discuss this if someone is interested. Soon, the new algorithm that were developed will be published in open source library, which is called LandLab. It's written in Python, and it's packaged for simulating surface processes and develop numerical modeling. So using the model, we ask three main questions. One, what are the conditions under which cliffs become buried or not? Second, how do changes in the restore properties affect the morphology of the cliff? And third, is there a distinct relation between the storm regime and the morphology of the system? So first I present parameter space, morphology of cliff slope as function of parameter space. On the x-axis, you can see rainfall intensity, and on the right axis, you can see grain sizes. So as you go from here to here, we increase the grain size, and from left to right, we increase the intensity. And we choose these two parameters to analyze the sensitivity of the morphology to them, because we know from field observation, first, that they are very, and second, that they are important. And focusing on two end members of this matrix, I will show some simulations. So on the left side, you can see a simulation with lower rainfall intensity but larger grain sizes, and you can see how a debris slope is developed with linear to concave profile, while in the other case, the cliff is repetitively undermined. You can see some collapses of material, and the total retreat is larger in this case. So we found high sensitivity of the model to rainfall intensity and grain size, as may expected. We know it from the field. Now we try to conduct another set of simulation of experiment, numerical experiment, using data from the field, from Ramon escarpment. So based on the rainfall statistics and grain size measurement, we conduct two typecast of scenarios. Now I'll present the result of the 2D version of the model. So we are looking, this is a map view, and you will look on the topography that evolved in this column. In this column, you will observe how the water depth within the domain is changed. And here you will see how the volume change, the total volume change from specific time step to the time step before. So this is a GIF of the simulation. So you can see that in the southwestern side, a smooth topography is developed with some debris cover that became deliver downslope and filled the channels, while in the northeastern side, the retreat distance is generally larger. You can see how the rills attacked the cliff line and make these small embayments. Also, the total volume that lost from this simulation is much larger than the total loss volume from the upper scenario. Using this kind of experiment, we can compare it directly, let's say qualitatively, not quantitatively, but we can do it directly with the landscape. So this is observation for Ramon escarpment, western side, and this is eastern side, and this is all model results. And you can see that the model captures some of the variety of the landscape with this linear slope and thicker debris cover, while in the northeast, we can see these vertical cliff lines and the heavily dissected landscape that somehow resemble the reality. The model predicts also other testable outputs, for example, changing in grain size. So this is grain size in phi scale, and you can see how the grain size, larger grain size concentrated on the rills, and this is less pronounced in the northeastern side, and we can now examine these maps, let's say, or the stream profile directly with field observation, and to see if it's true or not. Okay, the last set of analysis that I will present today is regarding changes in storm regime. And we know from present, under change in temperatures, that the intensity during high intensity, the rainfall intensity during high intensity storms is increases. And for the short duration, this increase in rainfall intensity for the short duration can be higher even the rate of the Cloud-Calperon scaling. Motivated by that, we conducted another set of simulations, now again with design storms, but now we change the temporal structure of the storm. For example, here we observe on a storm that is short, but with very high intensity, while the blue one is long with lower intensity, but they share the same total rainfall depth. So we are not changing the total rainfall, we are just changing the temporal structure of the storm. If it's getting shorter and intenser or longer and milder. And I will show some, we first change between the storm regime using some sine function. So whenever the red points will be above the blue points, this is, let's say, more intense regime but short duration, and the opposite for the other case. And in these two cases, I'm changing between this storm regime using different phase lengths. Here the phase length is about 2,000 storms, and here the phase length is only 200 storms. And here I just took a temperature record from Antarctica, showing based on the relationship correlating of temperature with rainfall intensity. I scaled the storm intensity by this record and tried to simulate them on the system. So what you can see is how the topography evolved. When the phase is longer, you can see the cliff is getting buried and the profile is getting complex, with some parts that are buried by debris and some parts that are not. And if you go to the very short storm period, the vertical cliff remains, and the cliff also retreats a longer distance. This is summarized by this figure that this axis is time, and this is the profile for different times. And you can see how the gradient of the cap rock here is much lower relative to the vertical face that remain in the right case. And this triangle represented the top of the debris cover, and you can see how it's alternate when the phase is long, and how it's retreating along the lithological contact when the storm phase is relatively short. And the last analysis I will show you is the same trick, using this kind of sign alternation between rainstorm regime, but over the 2D map, over the 2D model version. So we are get inside now low intensity phase, and you will see that the lower part of the slope are filled with sediment. And whenever we're gonna move to the high intensity phase that happens now, you will see that rills are evolving all over, and the cliff is pushed away and heavily dissected from the local, heavily dissected and go backwards from the local base level. So from this kind of analysis, we now can test if some hypotheses that were suggested by early studies, for example, these studies that suggested that transition from, let's say, wet condition to dry condition could change the morphology of the cliff, and to see if it's happened or not. And actually what we found for now, this is results that are still in progress, we are not finishing with this chapter yet, but what we found out that maybe for, let's say, at least in our cases, we show that it's not necessarily a wet and dry, but it can be low intensity or low frequency, and high intensity and high frequency, as we are not changing the total rainfall depth in our simulation, just the storm structure, temporal structure. Okay, so to summarize the last part, we examine what are the conditions under which cliff become buried or not, and the model mimic the sensitivity to cliff grain sizes and intensities, and I also have values for what condition the cliff will get buried or not. The second question was to how the storm alternating between rainstorm regime affect the cliff, and we found that this kind of alternation could produce complex cap rock profiles and change the cliff morphology. And overall, we found distinct relation between rainstorm regime and cliff slope morphology, with much more dissected landform during high intensity phase relative to the more smooth landscape in the low intensity phase, and this is although we didn't change the total rainfall at all. So taking everything together and to conclude, in the main chapter we started with observation of runoff and rainfall. We constrained the threshold for runoff generation and the frequency of local runoff and full extent runoff. And using experimental, numerical and physical experimental, we constrained the frequency of sediment mobilization. In the second chapter, we investigate changes in space in cliff slope morphology as function of hydroclimatic properties and mainly rainstorm regime. And we found that there is a high correlation of the morphology with the frequency of exceeding threshold for motion, which is much depends on the extreme storm and not in the annual condition. And in our last chapter, we developed a numerical model for modeling cliff and slope system in dry environment with explicit representation of hydrology. And this is now can be first to test prediction from the model, and also can be relatively easily implemented in worldwide study cases with real-world topography and real-world data of rainfall. And at last, we recognized the intrastorm intensity pattern and found that it has significant impact on the erosion pattern without changing the total mean. That's it. Thank you very much.
Questions?
Yeah.
The area
Yeah.
from above.
Mm-hmm. Let's say this one.
Yeah.
Good enough.
Yeah. You talked about the difference between the northern slope and the southern slope, and you attributed the differences in temperature because of radiation of the sun. But another possibility, maybe you consider it, is the fact that the southern arm is also facing where most of the rain is coming from. So maybe, whereas the northern is almost at the shadow of the rain. So maybe you have higher amount of rain, practical amount of rain, hitting the southern slope.
Yeah, that's definitely a good point. So I know that in some hill slope scale studies, these kind of differences can be found, but they are generally larger than this scale. Like this is about, let's say, 200 to 500 meters, so it's relatively small scale. So this is one point. And second point, this is actually true, but it cannot explain the large differences in grain sizes. So it's maybe also a process that enhances the exceeding of threshold of transport on the south-facing slope. But I guess that because that the grain sizes are much larger on the north-facing slope relative to the south-facing slope, it probably have a second-order effect. So the main order effect will be what are the classes that are actually, or the bedrock weathering pattern on the slope that govern, I think, more how frequent erosion thresholds are exceeded or not.
Anyone? I have two questions. From the model, you can calculate the retreat rate of a cliff. So, first of all, do these rates agree with directly dated ages of flat irons that were dated previously? And secondly, can you reconstruct, using this rate, the initial geometry of the Varamon crater? And would it fit what we think was the initial geometry 4 or 5 million years ago?
Yeah, so we can, in practical, we can do it, and it will be relatively easy, but in terms of modeling. But the hard part that we don't really have data yet in the Ramon escarpment in terms of dates. So we cannot, as you know, we cannot directly compare it to Ramon escarpment, but I done some simulation that trying to resemble Zug Tamrur escarpment or cliff, and the numbers are similar. I'm not showing it, but the numbers are relatively similar. Let's say that I'm conducting a numerical experiment, driving by the data, class size, and the cliff height, and so on of the Tamrur cliff. The numbers are similar, not exactly the same, but yeah, in practical we can do it. And in the Ramon we need to wait for the data. But yes, then we can estimate or reconstruct how Ramon escarpment is generally evolved in time. Yeah. And second question?
No.
That was the second.
Anyone else? Maybe someone on Zoom has a question?